You okay?
Yeah. Spring one springlet or something. With on top.
Hey, so All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good to hear. All right, so today it's a little bit early to present this, just because we still have a lot to cover that you need to use for the project. But I do have all the specifications and the starter code ready for the final project, so I thought we would discuss that today, just so that we can kind of go over it all together and just so that we're all on the same page in terms of what's expected. So we'll do that for maybe the first 30-45 minutes of class today, and then we'll go back to lecturing for the rest of class today. Okay. All right. I think that's about it. So homework, remember homework 3 is due this Sunday. So I know I've gotten a lot of questions on that, and I am a little bit behind on answering emails. I apologize. It's just been a kind of busy past couple of days. And so I will, answer all emails, tomorrow. I have a lot more time tomorrow morning to discuss. But I will definitely get back to you before the weekend. All right. Any questions I can answer before we get started for today? Okay. All right. So let's talk about the final project. So final project for this class is steady state heat conduction on an arbitrary two-dimensional mesh. Okay. So I know I've kind of been teasing the project kind of all throughout this semester, but basically the idea with this final project is that you're going to be writing your own finite element code in MATLAB to solve a problem like this. Okay. Now I've been training you guys up for this, right? And so we did our frame code, we did our truss code. In the first half of the class, we just finished talking about the 1D implementation of MATLAB just on Tuesday. And so this is going to be kind of the culmination of all of those things. Okay. Now the challenge, the biggest challenge that you're going to see on this one, especially compared to the other codes, is that your mesh here is going to be completely arbitrary. Okay. So you need to write your code in a way such that it can solve for the solution no matter how your geometry is meshed here. All right. And in fact, not only are you going to be responsible for solving this geometry, but you're going to be responsible for solving 2 other geometries as well, right? So that'll be kind of the real test to see if your code does what it's supposed to do, to see if it can solve basically any kind of geometry. Okay. So we are going to be using some special tools in MATLAB. So probably some tools that you've never used before. So we're going to use a toolbox in MATLAB called the PDE toolbox. And so that's what we're going to use to produce our geometries, to produce our mesh. We're going to use that to produce a reference solution so that you can kind of check your results. And so, first thing is you're going to have to install this onto your MATLAB. I believe all the computers in this lab have it installed, just because I always teach this class in this room, so they should still have it installed. But if not, it's very simple to install this. Okay. Okay. All right. So the main the main technique that we're going to be using for this project is called isoparametric elements, right? So it's still a couple weeks until we go over this, and so we do need to go over all the 2D stuff first. But isoparametrics is kind of the modern approach to doing finite elements. Okay, so basically the idea with isoparametric elements, it's kind of like a multi-dimensional version of Gauss quadrature, right? So the idea is that you have kind of an element here that's kind of arbitrarily kind of oriented in physical space. What you're going to do is that you're going to map it to a standard element, an element with known coordinates and known size, and then you're going to do the integration on this element here. Okay. So basically all that knowledge that we did in terms of changing variables, talk about changing the computing the Jacobian, changing the integration bounds, we're going to be doing that in 2 dimensions, right? And that's going to constitute kind of the main challenge for this project. Okay. Okay, so first part of the specification, and by the way, all of this is available for you to download on the Canvas website. So you can see I've created an assignment page for the final project on Canvas. You can download the instructions and the specifications here. There is starter code for you to download as well. There's starter codes for parts 1, 2, and 3. And then there is an example code for polyshape, which is something we'll go over later on today as well. Okay. There's also the rubric and a template for the final report that's available for you on mine as well. Okay. Okay. Okay, so these instructions here are just how to download the PDE toolbox, and so just make sure that you know how to do that. It's very simple. MATLAB basically just has its own version of an app store, and you just basically just say you want to download that one, and you can download it. Okay. Do note that if you are going to be using your home version of MATLAB, it does have to be at least the 2023 version of MATLAB, just because some of the tools that we're using were only put into MATLAB starting in 2023. And so if you have a version of MATLAB on your personal computers that you haven't updated in a while, now would be a good time to update it to I think if you download from MATLAB now, you'll get the 2026 version, but it has to be at least 2023. Otherwise, some of the tools that we use will not be available. So all the MATLAB in the lab classroom here is 2024, so it shouldn't be an issue for here. Okay. Okay. So this is the differential equation or the boundary value problem that we're going to be solving. So we have basically a two-dimensional heat transfer equation. So this is our diffusion term here. So you have second derivatives in temperature with respect to x and y multiplied by the thermal conductivity plus a source term here. Okay, and the source term for this problem is going to be fixed. It's just going to be minus 2500x plus 1500y. Okay. And you'll be basically implementing the solution to this problem on an arbitrary mesh. Okay. All right. And so, it's one thing to kind of say that, I want you guys to develop this whole code, but just saying that by itself is a little bit daunting. And so what I've done for you guys for this project is I've broken it into 3 different parts. Okay. And so the idea is that, by doing it in 3 parts, it's not as daunting of a task. And so part one, we're just going to do simple diffusion with Dirichlet boundary conditions. Part two, you're going to implement the source term. Part 3, you're going to implement the Neumann boundary conditions. Okay. And then by the end of part 3, you'll have a code that can kind of do everything that we've talked about in the class, right? And then part 4, you're actually going to implement it for an arbitrary geometry. Okay. Okay, but part 1 is probably the part that you're going to spend the most time on, just because there's a lot to implement for part 1. And so part 1, you're going to get a working code that's just going to solve diffusion with no source term and just Dirichlet boundary conditions. Okay. So actually, if you open up the starter code here, so actually let me open it up here for you to see. You'll see from the starter code here that I have the general structure of the entire code kind of already written for you. And so, you can basically just kind of just have to fill in the blanks for a lot of the code here, right? So if you open up the starter code, you'll see that a lot of this is written for you. So this is, a lot of stuff using the PDE toolbox, but you'll see that there are some things that some code you have to write yourself. So every code that I want you to write will be marked with to do, okay? So for instance, the first thing you're going to implement here is just, the specification of the Dirichlet boundary conditions, which you've done before, right? And so this hopefully should not be too foreign of a concept. This is something that, I've had you work on before, okay? Okay, so you'll be kind of implementing the Dirichlet boundary conditions. You'll be implementing the calculation of the element stiffness matrices. You'll be assembling the whole thing. You'll be applying the Dirichlet boundary conditions and the solution step here, okay? Okay, so if we go back to the instructions here, the instructions for part 1 will kind of walk you through kind of all of that, okay? Okay, so part 1, the goal with part 1 is to kind of keep it as simple as possible, to kind of implement just the bare minimum in order for you just to get a working kind of 2-dimensional code, okay? Okay, so here is a picture of your domain. So the domain that you're going to be working with is a simple L block. And I want you to kind of implement the solution on here, okay? First thing you're going to do is you're going to familiarize yourself with a lot of the data structures. And so there is a vector called nodes. And so this is a vector that contains all of the physical coordinates of all the nodes in your mesh. You have a data structure called connectivity, excuse me. So connectivity, this will tell you which nodes are connected to which elements. And so you remember we talked about that on Tuesday. Right? There are variables that tell you the number of nodes and number of elements, data structures for the global stiffness matrix, for the global forcing vector, and a data structure for all the element stiffness matrices and all the element forcing vectors here, okay? Now, the important thing to remember for this project is that, you're working with an arbitrary geometry. And so the mesh, for the most part, is going to be generated for you based on the element size that you're going to input into the code, okay? So these data structures that you have here for the nodes and connectivity, you're not going to be specifying this yourself, but you are going to be using them, okay? So, one nice thing about the PDE toolbox that we're going to use is that there's an easy way to kind of access the nodes and connectivity, which is kind of why I'm using it here, okay? All right. And so the other thing that you need to worry about here is that, you're going to need to do Gauss quadrature in 2 dimensions, okay? And so you need to define kind of where the Gauss quadrature points are going to be. Okay, and so if you kind of read through the instructions here, just kind of walk you through each section of the code that you have to write and exactly kind of which, what kind of the logic of each section is. And so, I'll kind of leave that to you here. And so a lot of this, again, is not going to make too much sense until we go over the multidimensional stuff. So over the next couple of weeks, we'll be kind of, going over the knowledge that you need to write this project. But I wanted to kind of get the specifications out to you just so that you can kind of read through them, so that as we are kind of learning about these concepts in the class, you can kind of be ready to apply them in the code right away. Okay. Okay. So part one, I think is fairly lengthy just because there's a lot to do there. You have to implement kind of all the bookkeeping stuff. You have to implement the element stiffness matrices, the assembly, the Dirichlet boundary conditions. So there's a lot to implement in part one. Okay. All right. Part two of the project is you're going to implement the thermal generation term, or the source. So part two, I would say, is fairly short. And so compared to part one, the addition of part two is not that great. And so you basically are going to be implementing the element forcing vector. That's the main contribution of part two. So part two shouldn't take you too long, but you do have to do some Gauss integration. And so, you want to make sure that you do that. Okay. Part three is also another kind of time consuming part. So part three is the implementation of the Neumann boundary conditions. Okay. Now, part three is going to be challenging because, unlike all the previous examples that we did, right? The Neumann boundary condition is not just going to be applied on a single point or a single element, right? The way we're going to apply the Neumann boundary condition is that we apply them along an entire edge, okay? And so along that edge, there is any number of nodes or elements that could be bordering that edge. It depends on your mesh, right? And so you need to implement the Neumann boundary conditions in a way such that it applies to every node or element that is on that edge right there, okay? And so I'd say, part one, probably time consuming from a conceptual standpoint. Part three is probably going to be time consuming just from a coding standpoint, just kind of understanding exactly kind of what's going on, understanding what the data structures actually mean. So part three, there is quite a bit to do here. So I kind of tried my best to kind of, explain all the different functions that you're going to use here. And so definitely, read the specifications carefully so that you kind of know kind of what you're doing. Just so that you kind of implement it in part three. Okay. Okay. All right. So that's part one, part two, part three. So by the end of part three, you'll have what I consider kind of a fully working code that can implement basically everything that we've talked about in class with regards to finite elements. So element stiffness matrix, element forcing vector, that includes both the thermal generation term as well as the Neumann boundary conditions, assembly, Dirichlet boundary conditions, solution, and plotting. So that to me is a complete code. So you should have that by the end of part three. Okay. Any questions on this so far? Okay. Part four. So part four is a part that I added just this year. Just because, in previous years, I think people just apply their codes to just one geometry and then just called it a day. But, ideally, the code that you write should be able to be applied to any geometry that you can think of. And so part four, I'm going to have you guys create your own arbitrary geometries and then apply your finite element codes to solve on that geometry. Okay. So to create your geometry, we're going to make use of another package within MATLAB called Polyshape. Okay. And so Polyshape is a package that lets you draw your own shape based on the coordinates. And then, use that as a geometry to solve a partial differential equation, okay? Okay, so the way it works is something like this. And so, let's say that you have an arbitrary shape, okay? So here I just kind of have a square domain with the square cut out. And so, you can use Polyshape to generate a geometry like this, and then use that to, solve your differential equation, okay? So the way it works is basically you need to define all of the vertices for your geometry, and then MATLAB will kind of connect those dots and create that geometry for you. Okay. So I have a couple of examples on how this works, right? And so in the specifications themselves, I've created this square geometry, so you can definitely read this code to kind of see how that works. Okay. But I've also prepared another file for you that will basically tell you how to create a geometry that mimics a letter. Okay. And that's the type of geometry that you're going to need to do. So the geometries that you're going to be making it's going to be different for almost everyone in the class. I did check and see that there's going to be no repeats. And so everyone should have, maybe your first geometry might be the same as someone else, but maybe not your second. But the two additional geometries that you're going to make is that you're going to make a geometry that matches the first letter of your last name, and another geometry that matches the last number of your campus-wide ID. Okay. And so the font that you're going to use is a font called Digital 7. So if you've ever had any kind of retro kind of digital clocks or digital watches, you might be familiar with this font here, which is basically a font that utilizes 7 lines to create different letters. Okay, and so you're going to recreate the first letter of your last name and the last number of your campus-wide ID using this font. Okay, and then you're going to run a finite element simulation on that geometry. Okay, so I know you might be asking, how exact does it have to be? It doesn't have to be that exact. You can see the example I used here, which is a P. And I checked, there's no person in this class with the last name P, so they're not seeing any P's on the final project. So you can see this P is probably the ugliest P that you've ever seen in your life. But something like this would work. Okay, so basically the idea with this part here is just to have a little bit of fun. You already worked really hard to write your finite element code. And so, I want you guys to apply it to an arbitrary geometry to show you that it should work for any kind of geometry. Okay. But that's the idea, right? And so the idea with polyshape is that you define all the positions of all the vertices for your shape, and then MATLAB will connect them for you. So for instance, here, I have the X, Y positions of all of these vertices here. So you would input that in the code, and then polyshape will make that shape for you and put it in a form that you can actually use for finite element simulation. Okay. Okay. All right. So that is the idea with the last part of the code. So, I would say in the specifications, this is the part that takes up the most space just because I have to explain how polyshape works. But hopefully this is the part of the project that takes you the least amount of time because you already have a working code. It's just making the geometry for it and then applying your code to that. Okay. Okay. Any questions on this? Okay, and then the final part of the project, so extra credit. So this is a very rare opportunity. I very rarely give extra credit opportunities, but this is kind of a good opportunity too, right? So for extra credit, and I'll give you guys maybe 10 points of extra credit for this if you get it. But I want you to submit another code where you improve the efficiency of the code itself. Okay. Now, the way that I've been teaching you guys how to write the finite element code, I think is a nice way to kind of go about it in terms of, kind of teaching you the first time. But the code itself is actually very poorly optimized. And so it utilizes way more memory than it has to. It utilizes more loops than it has to. So there is a way to kind of very much streamline the code and make it run much more smoothly. And in fact, if you were to improve the efficiency of the code, at least in the way that I'm thinking of, that is kind of the standard way that finite element codes are written, okay? And so because it's extra credit, I can't give you guys any more hints beyond that. But, just know that there is a way to dramatically increase the efficiency of the code, okay? So if you can do that and you can show me a code here that runs much faster, and there is a way that you can quantify it. So, you can basically quantify your code and you can time how long it takes for the code to run. And so if you can show me that your improved code does result in an increase in speed, then I will give you extra credit for that. Okay. So there's a little bit of a challenge there. It's definitely not required, to do this. You do need to have some programming kind of savvy, and so I don't want to make it a requirement for the class. But if you get done with the project early and you want to challenge yourself, this is a great way to do that. Okay. All right. And so the rest of these specifications here is just kind of what I expect you to deliver. So first thing I have just a summary of the different implementations of the code, right? So I've broken it down to, which parts of the code or which sections are written in which parts. And so you can see a lot of this is part one. There is a part for part, this should be part three, I apologize. So the Neumann boundary conditions is part three. But you can see kind of, and if you look at the starter code, you can see it's broken down into different sections. And so this is kind of when each section is implemented in which part, okay? Okay, deliverables. So these are the aspects that I expect in the results section of your final report. So there should be comparisons. There should be kind of parts of your final report that show me the results of part one, part two, part three. Okay. And the nice thing about part one, part two, part three is that I do output a reference solution for you, and so I do have a solved version of the solution for you to compare. And so you should see that when you do solve your part for part one, part two, part three, it should match with the reference solution very closely. Okay. So the first three things is just to compare, just to show me that the result that you get does in fact match up with the reference solution. Okay. Part four of the results is that I want you to perform a mesh convergence test. And so we'll be discussing what that is kind of later on in the class. Part five is, section five of your results is your results from part four. So basically just showing the result of the code applied onto your arbitrary geometries. Section six of the results is the bonus section. And so if you were able to update the code and improve the efficiency, this is where it goes. Okay. All right. And then so in terms of the things that you actually submit onto Canvas, you need to submit your final report. And so there's just a single PDF that I want for your final report. And I want your MATLAB code for all parts of the project. So that's part one, part two, part three. And I guess part four has two parts. So you can do 4A and 4B. Okay. All right. So that's all the code implementations that's required of the final project. Okay. So it is a lot of code to write, and I will give you guys time in class to work on it. So you would probably usually the last 2 or 3 lectures of the semester, that's usually when I end all the content. The last 2 or 3 lectures in the semester will be just project workshop, and so I'll come here, and then you guys can come here and work on the projects. If you have questions for me, you can ask for that as well. So it is quite a lot of code to implement, especially with part 4 now as well. So definitely you want to take advantage of those project workshop times. Okay. All right. Any questions on just any of the code implementations for the final project or any of the deliverables for the final project? Okay. Okay. So let's talk specifically about the final project components, right? So obviously a big part of your final report is going to be all the results, which you just discussed. Okay. But the other parts of the final project or the final report is that I want you guys to write it in the style of a scientific article, okay? And so I want you guys to write an introduction. So the introduction for an article like this is to basically just kind of give a brief introduction in terms of what the project is and what the objectives are, okay? Next part is the methodology. And so this is the part where I want you guys to explain the finite element methodology. Okay. Hang on, question in the chat. Or question in the chat. So for the extra optimized code will be submitted as a separate M file. Yes. Yes. And so if you do the extra part, you are going to submit an extra M file for that. Yeah. So keep parts 1, 2, 3, and 4 kind of separate. And then if you are going to do the bonus, just submit an extra M file for that. There should be, if you're going to do the bonus, there should be 6 M files that you submit. And so parts 1, 2, and 3, they're going to have their own separate M files. For part 4, there should be 2 M files for that because you're going to do 2 different geometries, so 4A and 4B. And then for the extra credit, that is a separate one. So that would be a 6th one. Okay. So the methodology part of the final report, I want you guys to detail all of the finite element methodology that goes into your final project. Okay. Now, this part's very important because I want you guys to write this section as if you were teaching someone about finite element methodology. Okay, so your intended audience for this would be maybe a fellow graduate student or maybe an undergraduate student that that does have some technical background but may have no idea what finite elements is. Okay, So in basically just one section of your report, I want you guys to be able to basically kind of give them a crash course in terms of what finite elements is and kind of what goes into it. Okay. I do want equations here. And so, I don't think you can explain finite elements without equations. And so I am expecting at least 9 equations in your final report in the methodology section that details, the buildup or the development of finite element, finite element methodology. Okay. So a lot of the lectures that we've gone over for the last, 4 or 5 lectures on boundary value problems, weak forms, finite element forms, all of that can go into your methodology section. Okay, I'll kind of leave it up to you guys, but it should kind of follow a logical progression in terms of developing the theory. Okay, and so remember, we don't have a final exam in this class. It's just the final project. But this is kind of the part of the final report where it kind of tests you and kind of see, how well you've been kind of following the content of the class. Okay. So this part of the report, the methodology, is going to kind of force you guys to kind of look at the course as a whole, to kind of look at kind of the path that we took to get to the end, and try to see if you kind of recreate that path or kind of summarize that path in kind of just your report, the methodology section. Okay. So try to really try to think of your perspective as like you're trying to teach someone about finite elements, and I think it kind of helps the methodology kind of go a little bit easier. Okay. Next section is going to be your results and discussion. So we just already discussed that. And then finally, your conclusion, where you just summarize your project and you kind of briefly explain what you learned from the project in the class. Okay. Now I do have a template for the final report. And so the template is here. Okay. And so it is a Word template. And so feel free to copy this into Google Sheets if you want, or Google Docs, right? The main thing is that, I do want you to keep the section headers. And so, don't delete those. That helps me in grading your reports to see the different sections. And so, make sure you have the section headers there. You don't have to use this font. I'm not attached to Times New Roman. It's just whatever happened to be, in the template when I typed it up. You can also play with the font size as well. I'm not too attached to the font size, but make sure it's readable. So don't use size 4 font, please. Make sure it's at least, 10, 11 font size. Can you use your own template? Yeah, absolutely. So if you prefer using Overleaf, if you prefer using LaTeX, absolutely use that. And in fact, if you could do that, I would prefer that actually as well, because it does make your report look a lot neater if you were to use LaTeX for that. The only thing I just ask is that if you're gonna use your own template, just make sure you include the same section headers. That's the main thing I'm looking for. Yeah, but this template is here if you want to use it. Mm-hmm. Okay. And then the rubric is here as well. So this is going to be the rubric I'm going to use to grade it. So when I do grade your final projects, I am going to grade it on this rubric. I will upload it to Canvas so you can take a look. But this is the criteria that I'm going to use. You can see how the points are broken down for each of the different sections as well. Okay. Okay. All right. So closing remarks. And so the last thing I'll say about the final project is that it is an individual project. So I don't mind if you work together with your classmates in developing the code, but I do expect everyone to write their own code. Okay, so there should not just be just a perfect copy and paste, from one person's code to the next. Okay, and so and you might say, how much differences can there be because everyone's essentially writing the same code. There are differences in how people code, and so I am going to be kind of looking at those. Okay. And and this kind of goes without saying too, but I mentioned this at the beginning, but I do want you guys to write your own code. Do not use any kind of outside tools, including AI, to help you develop the code itself. Okay. Okay. So final remarks, and so I am giving you guys this project very early, and so you can see that the due date is not until Sunday, May 17th, and so you guys have over a month to work on this, and so there is a reason for that, just because the project is going to be a lot of work. But I also want to give you guys all the opportunities that you can to reach out to me for help. Okay. So I recognize that it's MATLAB is not something that comes easy to a lot of people. It is something that I think is very daunting, especially when you say that especially when I'm going to have you guys write a lot of code for this project itself, right? I know there's going to be a lot of coding involved, but that doesn't mean that you can't ask me for help or ask your classmates for help. Okay. But the hope is that, by the time you finish this project, that this is something that you can use as like a portfolio piece. And so, you can go to, let's say you can even try to apply for a job at ANSYS and say that, I took a class in this, I developed my own code. That is something that's very impressive. That's something honestly that not a lot of people have done. Even for people that have taken a finite element class, not that many people have written a code as extensive as this that can solve on an arbitrary geometry like this. Okay. So it's a lot of work, but I do want this to be something that you guys are proud of, something that you kind of always remember this class. Okay. All right. Any final questions on the project before we jump back to the lecture? Okay. All right. And so that's the project. And so that'll be available to you guys. So again, I think a lot of the project will start to make more sense in the coming weeks as we start to go over 2D finite elements, as we start to go over isoparametric elements. So over the next couple of weeks, I think things will make a bit more sense. Okay. Okay. So let me go back to the lecture notes here. Should have joined on my iPad from the beginning. We'll wait for this to load. Okay. All right. So the topic for today and kind of the topic that'll take us all the way until the end of the semester is multi-dimensional finite elements, or I should say multi-dimensional boundary value problems. Okay. Okay. So these are the learning objectives. Basically, today, the plan for today is just to give you guys an introduction to the mathematical preliminaries that we need for 2D and 3D finite elements. Okay. And then on Tuesday, we'll actually start to get into, weak form solutions, finite element form solutions, all that good stuff. Okay. Okay. But for today, we're doing mathematical preliminaries for 2D FEA. All right. So everything we've done in this class, all the way from the beginning, has kind of been building up to this particular topic here. And it's a very important topic because, basically all modern finite element codes are built on the theory that we're going to go over the next few weeks. It just takes a while to get here just because there's just so many concepts that we have to do. Okay. Okay, so basically the idea, starting today up until the end of the semester, we're going to be extending what we know about 1D finite element boundary value problems to 2D and by extension 3D as well. So that's our goal. Okay. So, we're not explicitly going to get into 3D in this class, just because when you get into 3D, it becomes even more untenable. But a lot of the concepts and a lot of the equations that we're going to develop for 2D, it's actually it's much easier to jump from 2D to 3D, whereas going from 1D to 2D, there's a lot of extra things that you have to consider. Okay, so we're going to focus on 2D, but just know that a lot of this theory applies to 3 dimensions as well. Okay. Okay. So the biggest difference when you go from 1D to 2D is, obviously the extra dimensions. Okay. Okay. So that has a lot of consequences. And so on the one hand, that extra dimension is going to require us to account for that in our differential equations. Okay. So instead of an ordinary differential equation, which are equations that we can essentially solve by hand, we are now dealing with partial differential equations. Okay. So partial differential equations often we call PDEs. And so if you ever heard the term PDE, that's what it refers to. Okay. Now the sad thing about PDEs is that we don't have very many great methods to solve them. In fact, I would say very few of them are solvable. Only the simplest PDEs are solvable. Right. So that means we do have to rely on finite elements, but that is a good thing. And so finite elements does give us a way to solve for these PDEs. Okay. Right. So that's a good news. So the good news is that we have a problem we can solve. The bad news is that because these are PDEs, it's much more difficult to get a reference solution. And so if you think back to the code we wrote on Tuesday, right? The way that we verified that our solution was good was that we verified it against the exact solution, right? We're not going to have that luxury available to us anymore. And so we're basically you can think of it almost like we're shooting in the dark here, right? Okay. A lot of times, when you're running a finite element simulation on a system that's governed by PDE, I think there's a legitimate question that you can ask, and this is not just code that you write yourself, right? This is maybe simulation that you run on ANSYS. And so you would think that a commercial software like ANSYS would give you reliable results, but that may not always be the case. And so there will be some situations where maybe the physics of your situation are too complex to handle for a finite element code. And so, you may not get an answer that is consistent with reality. Okay. And it's much harder to verify that, much harder to validate that to see. Okay. And so we are going to discuss this. This will be kind of the last thing that we discuss in this class. It's called verification and validation. That will be almost the very last thing that we cover. But I do want you guys to keep that in mind that when you are running simulations on 2D, three-dimensional phenomenon, it's much harder to check your results. Okay. The other consequence, kind of mathematically, from going from 1D to 2D, is that now we have to introduce concepts of vector calculus and vector algebra. Okay. So a big part of today is just going to be a review of vector calculus and vector algebra. So, hopefully things that you've seen before, but we do have to kind of go over these concepts as they kind of form the basis of a lot of the mathematics that we're going to do. Okay. Okay, but that's the idea, right? And so, basically take the same methodology. So, it's not like we're coming up with a brand new method. So, we're applying the same methodology that we've been doing, but just applying it to arbitrary 2D, three-dimensional problems that are governed by partial differential equations. Okay. All right, any questions on this? Okay, all right, so let's start with just some basic definitions. Okay. All right, so first let's kind of remind ourselves what a boundary value problem is. So remember, a boundary value problem is such a problem that solves for the governing equation on a particular domain. Where the solution is subject to boundary conditions. Okay. So that's exactly the same definition that we had for one dimensions. Okay. But of course, the way that we interpret several parts of this are going to change because we are moving up from 1D to 2D. Okay. Now I'm going to highlight, remember, the three main components of a boundary value problem. Okay. So first we have the governing equation, right? So we just finished talking about the governing equation, which is now a partial differential equation. Okay. We also need to have a geometric domain, and so we'll talk about that in a second. And then the last component of a boundary value problem are the boundary conditions. Okay. Okay, so let's go through these one by one, and then talk about how they generalize in multiple dimensions. Okay. Okay, so let's talk about the geometric domain. Okay. So in 1D, right? In 1D, our geometric domain was simply just a line, right? Right, very straightforward, right? So, in one dimension, we can only go in one dimension, and so we have a line, okay? So in 2D, right, once we kind of add a second dimension, then actually a lot of things open up to us, right? So instead of being a single line, our domain is comprised of what we call a surface. Okay? And so the surface can have arbitrary shape, and so there's no restriction on the shape that our two-dimensional domain can do. Just like we talked about, with the final project, you can solve on any two-dimensional domain. Okay. And then in 3D, our domain is in 3 dimensions, which is a volume. Okay. Seems very obvious, but it's worth kind of stating that this is what it means to go from 1D to 2D to 3. Okay. Okay. Now the other interesting part here is how we talk about the boundary. Okay. Right. So for all cases here, we can talk about what the concept of a boundary actually represents. So in 1D, when we talk about the boundary for 1D, we're talking about points, right? right? So the boundary of a one-dimensional domain is just the two endpoints. Right, so that's what we've gone over. That's kind of what you guys are working on for the homeworks, right? So you apply the boundary conditions at those endpoints right there. So there's just one specific location where you apply one boundary condition, one specific location you apply the other boundary condition. Okay. Okay. For a two-dimensional surface, the boundary is comprised by a line. Okay. So if your domain is two dimensions, if your domain is a surface, then it's bound by a line that goes around the edges. Okay. And then for three dimensions, the boundary is a surface. Okay. Right? The boundary for your three-dimensional domain is essentially the shell that goes around your three-dimensional wall. Okay. Now you should notice a trend here that for a given dimension, the boundary is defined by the domain that is one dimension lower, right? So the boundary for a two-dimensional domain is a one-dimensional construct, and the boundary for a three-dimensional domain is a two-dimensional construct. Okay. So the boundary or the concept of a boundary on your domain is always going to be one dimension less than the dimension of your domain itself. Okay. Right. The exception, of course, is 1D. So there's, I guess you can say a 0D construct is a point, but it's not really that as well. Okay. Now this is going to be important because when we do solve our problems in 2D, right? When we apply the boundary condition is not going to be just applied on a single point. It has to be applied across the entire boundary. So that has important implications for our code and for our solution. Okay. So that means that when you do apply boundary conditions, and you'll see this on the final project, that you are going to have to write a loop to loop over all of the nodes and all of the elements that border the boundary. Okay. So the concept of domain and boundaries is going to be very important, especially once we get to the math, right? You're going to see that, for certain integrals of our weak form, for certain integrals of our finite element form, they're going to take a certain form because they either are applied on the domain or on the boundary. And so kind of understanding these differences is pretty key. Okay. All right. Any questions on this? Good. All right. Another important concept for the boundary that we need to go over is the concept of an outward unit normal. Okay. Okay. So let's look at a two-dimensional boundary just as an example. Okay. So we've already kind of established that for a two-dimensional surface or two-dimensional domain, our boundary here is a line, right? Now, along that line, we can draw vectors on that line that point outward from the domain. Okay? You can do this at every single point on the boundary. Okay? So these vectors here are called the outward unit normals. Okay? And so usually we give them the symbol n hat. Okay? So n hat is a unit vector that is defined on the boundary of the domain. Okay? And it always points outward from the interior of the domain. All right, so the outward unit normal will actually be a big part of our solution of our equations. So this is a concept that you should be familiar with. Okay. In particular, a lot of times in our solution or a lot of times in our equations, we're going to take the dot product between some vector and the outward unit normal. Okay. Okay. So in other words, we'll have situations like this where we have some vector v. We take the dot product with our normal vector n. Okay. Okay, and so just to kind of remind you, when you take the dot product between two vectors, you essentially get the component that is shared between the two vectors. Okay. Okay. So let's say that you have an outward unit normal that goes like this, right? And you have another vector, let's say it goes like that. Okay. The dot product between them will be the amount of v that's pointing in the n hat direction. Okay. All right, so basically you can project like this. Right, and so in blue right here, we have v dot n. Okay. So you're going to see this a lot in our equations for our partial differential equations for our weak forms. And so it's important to kind of know exactly what that physically kind of represents. Okay. Okay, good. All right, so far, we've covered, multidimensional domains, multidimensional boundaries, the outward unit normal, right? All of these are important concepts for us to know. Okay. Next thing we'll cover, just along the lines of a partial differential equation. Let's review just the idea of a partial derivative. Okay. And so in multiple dimensions, our variables are going to be a function of, well, multiple variables. Okay. Okay. So even in two dimensions, our function is going to depend on both x and y. Okay. All right, so let's say we have a temperature field that is, we're going to spend a lot of time talking about heat transfer. Our temperature field can depend on both x and y. Okay. And so because we have two independent variables here, we can take a partial derivative in each of those directions. And so we can take partial t, partial x, and then partial t, partial y. Okay. So these are what we call partial derivatives. And so each partial derivative basically tells you how your function or how your function t is changing in that particular direction. Okay. Right. So just because by being a function of multiple variables x and y, it can change in the x direction, it can change in the y direction. Okay. Okay. All right, so today is just going to be a rapid fire of vector calculus concepts. So now that we kind of have reviewed the idea of a partial derivative, we're now ready to start talking about some common vector calculus operations. Okay. Okay. And we need to review these just because they're going to show up in our equations. Okay. Okay. So the assumption here is that we have some function t that's going to depend on multiple space variables at the same time. Okay. So all of the examples that we'll do here assumes that we have some function t that changes in x and y. Okay. So I'm going to define some very common and important vector calculus operations based on this t. Okay. So first one that we're going to define is what we call the gradient operator. So the gradient operator is, you can think of it as kind of like an expanded derivative, where you're going to take the partial derivative of your function in every direction. Okay? And then you're going to store that result into a vector. Okay, so the symbol for the gradient operator is going to be an upside down triangle, which we call a nabla. Okay. So this upside down triangle here is called a nabla. Okay, so let's, I forgot my symbol already. We're using the symbol t. Okay. So if we take the gradient of our field t, this is equal to partial t, partial x, comma, partial t, partial y. Right. So you can see here from the gradient that we know that t is a function of both x and y, right? And so it can change in both of those directions. And so when we take the gradient, right, we are measuring the rate of change of t in the x direction and the rate of change in the y direction by taking their partial derivatives and then storing the result into a vector, okay? Now, the most important part of the gradient is a part that, I kind of glossed over here, right? And so the gradient, I always think of the gradient as adding a dimension onto your result, okay? So the function that we started with t, this is what we call a scalar quantity, right? Right. So a scalar quantity is one where it just has one value stored at every unique x and y location, okay? But when you take the gradient of a scalar quantity, you get a vector. Okay. Right? So you take the gradient of a scalar, you get a vector, right? And you can take the gradient of a vector as well. And so if you take the gradient of a vector, then you get a matrix. Okay. So what happens when you take the gradient of a matrix? You get a three-dimensional matrix. And when you take the gradient of a three-dimensional matrix, you enter the fourth dimension and just everything breaks out the wall. But we won't go there. We'll just do scalars to vectors. Okay. Okay. Good. All right. Next thing that we'll go over, our next operator is called divergence. So the divergence is another operator that you can take in vector calculus. Okay. And so divergence kind of does the opposite, where the gradient goes from a scalar to a vector. Divergence goes from a vector back down to a scalar. Okay. And so the divergence is you basically take the dot product between your nabla and a vector quantity, and you obtain a scalar from that, okay, because of the dot product. Okay. Okay, so for instance, okay, so divergence is often portrayed like this. And so you have your nabla operator, you have your dot product, and you have a vector, okay? Where this nabla operator, I should have defined this up above. This nabla operator you can think of as a vector or a pseudo vector, which has components in the x and y directions, okay? So nabla here is going to be partial x, partial y, okay? And this u also has to be a vector as well. So let's say that this has a component in the x direction, ux, and uy. Okay. All right, so you take the dot product between these two, you get partial ux, partial x, plus partial uy, partial y. Okay. So because of the dot product operation there, you are basically summing up each of the components of the different, of both the nabla and the vector. And so what you end up with is a scalar. Okay. Because all of those components are just kind of added together to form the scalar. Okay. All right. So we have the gradient, we have the divergence. Last operator that we're going to look at is technically the combination of the two, which we often call the Laplacian. So for the Laplacian operator, if you take the divergence of the gradient of a scalar field, okay? So you can kind of follow the logic a little bit, right? So gradient takes a scalar, turns to a vector. Divergence takes a vector, turns it back to a scalar. So the result of this is going to be a scalar, okay? So you might think that, we're just kind of going in circles here, but each time that you apply one of these operators, you are going to add an order of derivative, okay? So when you take the divergence of the gradient of a scalar, you do get a scalar, but that result has second order derivatives associated with it. Okay. So let's kind of break it down. So let's say that we have your scalar function t. You take the gradient of that, okay? And you're going to take the dot product with the nabla, right? So we've already seen the gradient of t. So we know the gradient of t is partial t, partial x, partial t, partial y, okay? We know nabla here is partial x, partial y, okay? So you take the dot product between these two, right? So you're basically going to apply a second x derivative to the first term, a second y derivative to the second term, and what you get is partial squared t, partial x squared, plus partial squared t, partial y squared, okay? Which you can see is a scalar. Okay? But it's a scalar with second order partial derivatives. All right. So again, kind of a crash course in vector calculus, but these are important concepts. We're all kind of building towards something. It kind of seems like we're just kind of going over a bunch of random concepts here. We are building up to something that's going to be important that we're going to use. Okay. Any questions on this? Okay. All right. So last topic that we'll go over, and I think we are probably going to finish it up on Tuesday, um, is Green's theorem and Green's formula. Okay. Okay. So everything we've gone over to this point are just kind of the basics, right? Now let's actually see how that actually applies to our finite element methodology. Okay. Okay. Actually, we're not quite there yet. So let's go back to our weak form, right? Okay. Okay. So if you remember from the weak form, there was kind of one really crucial step that we had to do in order to get our weak form into the form that we know and love right now. Okay. So there's one part where we applied integration by parts to balance the derivatives inside our integral. Okay. And this was key, right? Because remember, one of the nice features of our boundary value problem, or the weak form that we liked, was the fact that we had no derivatives higher than first order. And so performing that integration by parts was a very important part of that process. Okay. So just to kind of summarize what that looked like, right? So we had our integral from 0 to L, W of x, e times a, d squared u dx squared, right? So just for the sake of clarity, I've assumed that e times a does not depend on x, and so I've applied the second derivative to u, okay? And so by applying integration by parts, okay, we obtained two terms from this. And so we obtained one term, which was still an integral, right? So it was still an integral from 0 to L of dw dx, e times a, du dx, dx, okay? Right? So this first term, even though it was still an integral, it had balanced derivatives, right? And so we basically moved one derivative from the solution over to the weighting function. Okay. Right. And then to this, we added an additional boundary term that contained our Neumann boundary condition. Okay. We had w of x, e times a, du dx, evaluate at x is equal to lambda h. Okay. So this right here, this was our Neumann boundary condition. So this was very nice, right? And so by performing this integration by parts, we got our equation, or we got our boundary value problem into a form that had much nicer properties than what we started with, right? Okay. I think the most obvious nice property that it has is that we only have first order derivatives, and so we took advantage of that right away. And so when we did our finite element solutions, we assumed that we had linear functions, and so that led to the finite element solutions that we had before. Okay. The other nice property is that the Neumann boundary condition is implemented directly into our equation here. And so it's not something that we had to apply separately, like the Dirichlet boundary condition, okay? It's just baked right into the equation itself, right? So ideally, we would like to do this for our two-dimensional problem. Okay. The issue is that we need some new mathematical tools to do this integration by parts, quote unquote, okay? Because our equation now, remember, is not an ordinary differential equation. We now have a partial differential equation, right? And so let me kind of write the equation down, and we'll kind of motivate the issue, and then we'll call it for the week, and we'll continue next week, okay? So our heat equation in 2D has the following form, right? So it's partial squared t, partial x squared plus partial squared t, partial y squared is equal to, or I should plus s of xy is equal to 0, okay? Where s of xy there, that is our thermal generation term. That is, what we saw from the final project, right? A common way that we can represent this, this should look familiar. This was our Laplacian operator that we just finished talking about, okay? So we have Laplacian of our temperature field plus our thermal generation term is equal to 0. Okay. And so to generate our weak form, we are once again going to integrate this. But since we're in 2 dimensions, we are going to integrate, we're going to do a double integral. Okay. With respect to area, so we're going to integrate it over the entire surface of our 2-dimensional domain. Okay. And so the main challenge that we are going to see next week, right, is we need to take this integral here, right, which very obviously has second order derivatives, right? Remember, we don't want second order derivatives. Those are not nice because we want to have a linear shape function. So how can we take this double integral here, apply integration by parts, and get a result that looks similar to this? Okay. Oh, I forgot the weighting function. We do need weighting functions here too. Because the derivative has to go somewhere, so it has to go onto our weighting function. Okay. All right, but that's what we're going to do on Tuesday. So when we come back on Tuesday, we'll finish up this derivation of Green's formula, and we'll see how we do that integration. And then we'll use that as kind of the backbone for our foray into 2-dimensional heat conduction using finite elements. All right, so thank you guys for coming today. Hope you guys have a good rest of your day. Hope you guys have a good weekend. I will get to you. I know a lot of you have sent me questions on the homework. I will get to them tomorrow, I promise. And even the ones I have answered, I haven't really had a chance to really look at them. So I promise you I will get to them tomorrow. So send me your questions. I will get to them tomorrow morning. And I will see you guys next week. Thanks, Christina. You too.
I'm sorry, James mentioned to me. Yeah.
Yeah.
I'm sorry, when was the midterm?
Midterm is 2 weeks from today.
From today.
Yeah. So that's April 23rd.
For me, because he's graduating. Thank you so much.
Yeah.
Just the registration dates and like what classes. Yeah. He mentioned them in the, he just told me like, he just, that's old, but. Yeah.
Look, I don't know if he teaches them that.
All right, Zoo people, any final questions before I wrap it up?
Have a good weekend.
See you, Lowell. See you guys.
See you, Professor.
All right, see you guys next week.